Okay, going over the free response portion of the practice semester 2 final. So the first question here says, what is the delta H of reaction if a certain amount of energy is released when you get 30.5 grams of C3H8O? So the delta H of reaction, what you want to do is set up what you know. So you get the amount of energy over the amount of chemical, but it's in grams, so we want kilojoules per mole. So we're just going to calculate up the molar mass and figure that's in moles. But we have one more step, and that is we have to take into account the fact that there's 2 moles of C3H8O. Okay, and so there's 2 moles of the chemical for every 1 mole of reaction. So when I get all done, I get 4,040 kilojoules per mole. But one thing I also kind of almost forgot was this negative sign, because the energy is released. And when you do all this, you kind of really don't get the amount of energy. Although I guess you could have said that's negative 1025 kilojoules for energy release, and then that would remind you it's negative when you're done. Okay, letter B is enthalpy of formation. So back here to our whole reaction, okay, it's going to be products minus reactants. So it's going to be these 2 chemicals over here minus these chemicals over here. And we're given numbers for CO2 and H2O. O2 is 0 for delta H formation. And this guy here is going to be X, okay? And we're going to use our delta H of reaction as this number. So I set it all up. So my products minus reactants. And then I said, okay, so 6 times the delta H of formation of CO2 plus 8 times the delta H of formation of water minus 2 times delta H formation of C3H8 and 9 times the O2. And I'm not worried about that because that's going to be 0. I substituted my numbers, and there's my X. And after that, it's just an algebra problem. So I carefully work, and I got negative 306 kilojoules per mole. We had positive 306 on the answer key, and it's been changed. Okay, number 2. Given the following reaction, okay, this looks like a rate law problem, but the first thing is, what's the rate of disappearance of ammonia? So this is given as the rate of appearance of N2H4, and we can see it's a 1:2 ratio, so our answer is going to be in a 1:2 ratio. So we have 3.6 moles per liter per minute, and because of the reaction, there's 1 mole of N2H for every 1 mole of NH3. And so it's going to be 3.6 times 2. So on the key we have negative 7.2 moles per liter per minute. That would be the rate. Or I think you can just say it's 7.2 moles per liter per minute that is disappearing. You know, so with the word it kind of takes the place of the sign. So either of these would be good. Now the rate law for this reaction. So the basic rate law is just going to be rate equals K times the concentration of the reactants raised to some powers. Then we look at the chart up here, and so I looked at number 1 and 2, and I saw this guy is not changing. This one is going up by 3, and when it does, my rate went up by 3, and I just divided my larger number minus my smaller number. So if the concentration of the H2O2 goes up by 3, and the rate goes up by 3, then I know that the order for H2O2 is 1. So when I put it in my final rate law, I don't need to write that. Now the other one, I'm going to go ahead and say, looking at 1 and 3, so 1 and 3, that doubled, okay, while that stayed the same. And when that doubled, my rate quadrupled. Again, 14.4 divided by 3.6, that's 4 times. And so if my rate doubles and if my concentration doubles and my rate quadruples, then I knew that my order is 2. So putting that in, rate equals K times the concentration of NH3 squared times the concentration of H2O2. That's my rate law. Now continuing on, find the value of K. So I wrote my rate law again here, and then I'm just solving for K. And then now I just take any trial, okay, and I put the numbers in, and I did my rate over my concentration squared and my other concentration, and I just put those 3 in and solve, and I got 3.6 times 10 to the 6th, and then this is moles per liter per minute over moles per liter, and moles per liter. So when I'm all done, it's moles per liter to the -2, minutes to the -1, or you could write that as 1 over moles per liter squared minutes. Letter 4, what is the rate of a disappearance of N2H4 if NH3 is a certain number, H2O2 is a certain number. So now we're just going back and using the rate law again, but we're just going to substitute in. So we calculated our K, that goes in. Here's our concentration squared, and here's our other concentration. And just, substitute in and evaluate, and we get, I got 0.52 moles per liter per minute as my answer. Okay, going on to a little bit of equilibrium. Okay, here it says write the expression, and these are all gases, so I just put everything in. So here's the KEQ expression, pretty simple. When you say KEQ expression, be sure to include the KEQ equals. Don't just put the fraction. For the next one, experiment 1, a reaction mixture is found to contain blah, blah, and blah. In which direction will the reaction shift? So if we're saying which direction it's going to shift, that means we have to calculate a Q, and we're going to compare it with our K. So if Q is less than K, it shifts to the right. If Q is greater than K, it's going to shift to the left. So I just rewrote my K expression and called it Q, because I'm not putting in equilibrium values and just putting in my test values. Substitute my values, don't forget to square the 0.38, and I get the answer 361. So 361 is less than 841, so Q is less than K, it's going to shift toward the product, shift to the right. Now for part C, it says now what are you going to get at equilibrium? So doing part B is actually helpful here, because when we set up our ice box, and I just rewrote my equation, substitute in the original numbers from the last problem, and I can say it's going to be minus x plus 2x because of the coefficients. And then I get my expressions here for this part. Then I know that it shifted to the right. We just calculated that. So I know that this is minus x and is plus 2x. Okay, and then I go over here and say I'm going to use my K expression. So the KEQ is equal to my product, this expression squared over this expression, and it's the same twice, so it's squared. So my little solving trick is to take the square root of both sides. So the square root of 841 is 29, and the square root of those things squared is just those numbers. So now it's algebra. So I went through the steps and multiplied over, blah, 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 subtracted, get things to say. So I have x, and I get a value of x of 0.00645. When I go back and put them into my 0.02x, 0.02 minus x and 0.02 minus x and 0.38 plus 2x, I get those three values, and those are all molarities. Okay, letter D, we have another experiment. Okay, we know the H2 concentration, we know the Cl2 concentration, find the HCl. So again, we know this is 841. So 841, this is going to be called x squared over 0.008. And then just solve for x. So x squared is this number, x is 0.232 molar. It's just an algebra problem. Now going on to number 4, the vanadium. Vanadium is element 23. Look on the periodic table, and you can see it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Short form, okay, all of this rest are here is like argon, so argon, 4s2, 3d3, and those are my two valence electrons right there. Everybody in the middle there, anybody in the transition metals has two valence electrons. Now, write the short form electron configuration, okay, so of the vanadium ion. So first off, again, I'm going to write my neutral. So my neutral is argon, 4s2, 3d3, and I'm going to lose 3 electrons, and we lose those 4s electrons first, and we're going to lose one of our d electrons. So my final answer is argon 3d2. Now we're explaining. Okay, so vanadium and niobium. So I find them on the periodic table, and I see that they are one on top of the other. So what's the same about them? The same, they're in the same column. They each have 2 valence electrons in their orbitals. What's different about them is that the valence electrons for vanadium are in the 4s, wherein for niobium they're in the 5s. And since niobium's outer electrons are in a higher orbital, it's going to be farther from the nucleus, which makes it larger. For letter D, the ionization energies for vanadium and chromium are given, and we can see that the one for chromium is a little bit higher than the one for vanadium. So explain. So then here I look down the periodic table and see these are next to each other, and that makes a difference. So what's the same? They're in the same shell. They both have valence electrons in their 4s orbital. What's different is chromium has 24 protons, vanadium only has 23 protons. So if you have a greater number of protons, then that is going to attract those outer electrons and make it a little bit more difficult to pull them off. So that's why this guy is a little bit higher than that one, but not very much. Okay, number 5, we're doing our Lewis dot structures. Okay, so first off, okay, CO. Now CO, I would have done this where I give everybody an octet. And I say, well, C has 4 valence electrons, oxygen has 6 valence electrons, that's 10, but I've drawn 14. So I got to take away a pair, make these share, take away a pair, make these share, and then when I get my correct value, it looks like this. So I have triple bonded carbon and oxygen, and those are not very similar electronegativities, so it's going to be a polar molecule, which is important. I should recognize here that CaO is an ionic compound, metal and nonmetal, so I'm not going to try to write a dot structure like this. Okay, what I want is just draw my 2 different ions like that. So the calcium ion, no electrons, oxide ion, 2 of 8 electrons. So the type of solid, this is molecular, and this one's ionic. The interparticle forces, okay, here it's a polar molecule, so it's dipole-dipole interactions. And the interparticle forces, we can call it ionic forces or ion-ion forces. Anything that says ion will know that. Okay, for 6, we have some different compounds here. So here's Bi3. B is one of those chemicals that does not follow the octet rule, so it only has 6 pairs of electrons around it. And SF2, okay, S, can usually form 2 bonds. Okay, it can also do other stuff, but right now it's going to form 2 bonds, so kind of like a water molecule. The molecular shape, okay, this guy here is steric number 3, trigonal planar, and this guy is tetrahedral with 2 lone pairs, so it's going to be bent. Bond angle here is 120. Bond angle here, okay, roughly 109.5, but because of these lone pairs, then it's going to be smaller. So, if we said it's like about 104 degrees, that is perfectly good. But, if you said 109.5 or a little less, that would be great. Okay, this molecule here is very non-polar. Okay, trigonal planar, very even looking, 1, 2, and 3. So even if there was any kind of a dipole, they would cancel out. So it's a non-polar molecule, therefore London dispersion forces. And for the other one being bent, and we know that if we have, lone pairs on that central atom like that, they usually bend the molecule, make it off-center. So one side would be a little bit negative, the other side a little bit positive. Polar molecules, dipole-dipole interaction. It is not going to be hydrogen bonding because you'd have to have hydrogen bonded to nitrogen, oxygen, or fluorine, and we don't have that. Okay, 7. Gas sample with H2 and O2 gases. The partial pressures of the gases are 0.6 and 0.9 respectively. If there's 0.05 moles of H2, find the moles of O2. Well, we have our Graham's law of effusion, which talks about, the moles over the total moles equals the partial pressure of a gas over the total pressure. But what that really means is that all these particles can cause the same pressure. So the more moles you have, the more pressure you're going to have, partial pressure. So we can actually set up our own little proportion here because it's proportional. So the moles of hydrogen over the partial pressure of hydrogen is going to equal the moles of oxygen over the total moles of oxygen. So I just set that up, 0.5 over 0.05 over 0.6 is equal to x over 0.9. My pressure went up 1.5 times, so my moles must have gone up 1.5 times. So it's 0.075 moles of oxygen for my answer. Now it says here H2 effuses at 550 milliliters per minute, and effuses just means escapes, and it's proportional to the velocity. Find the rate of effusion of oxygen. So we're saying, well, if I know one of these, I know this guy, and I know their molar masses because I know what the chemicals are, so I can get 3 of these and plug it in and get the last one. So I just did the square root of the molar masses of H2 over O2, and I get 0.251. So 0.251 is equal to x over 550, and solving that I get 0.251, I'm sorry, equals, so 550 times 0.251, I get an answer of 138 milliliters per minute as my rate of effusion. And that's the entire test. I found this little graphic on the internet, and I thought it was kind of nice. So you're here, working on this test, going over these answers, and it's not that easy. You have a lot of, in-between work here to do. So, going through these answers and figuring out why they are what they are, that's what you need to do in order to get success. Good luck.